This will be the lecture over chapter 22. Here we're going to be looking at alternating current and what are the characteristics of the properties of working with alternating current. So in order to be able to describe alternating current, we have to come to an understanding of what phasors are. So let's take a look here at the summary, and then we'll go into specifically here what phasors are and what they mean for us. All right, so we've got an AC source, and we know that produces an EMF that varies sinusoidally with time. So a sinusoidal voltage or current can be represented by a phasor, a vector that rotates counterclockwise with constant angular velocity, omega, equal to the angular frequency of the sinusoidal quantity. So the projection right here along the horizontal axis in any instant represents the instantaneous value of the quantity. So in other words, as this rotates around like this vector here is going to bounce over here and then bounce, shorten up, get real short, go over this direction, then come back and go this direction and come back. So it's going to be bouncing constantly like this along the x-axis. And the projection on the horizontal axis at any instant represents the instantaneous value of that quantity. So for a sinusoidal current, I, with maximum value of capital I, the phasor is going to be given by this. Now with power calculations, it's useful to use the root mean square value, which is capital I divided by the square root of 2. So let's go and let's take a look at that. Okay, so we got a source of alternating EMF that can supply an alternating current to a circuit. So we've got a coil of wire rotating with constant angular velocity in a magnetic field, and it develops a sinusoidal alternating EMF and is the prototype of the commercial alternating current generator or alternator, just like the alternator you've got in your car. An LC circuit can be used to produce an alternating current with a frequency that may range from a few hertz to many millions of hertz. So we'll use the term AC source for any device that supplies a sinusoidally varying potential difference, V, or current, I. A sinusoidal voltage may be described by the function like this, just like it was with the current. We're going to replace that with voltage. This is going to be the maximum potential difference, which is going to be called the voltage amplitude. This is going to be the instantaneous potential difference, and omega is going to be the angular frequency, equal to 2 pi times the frequency, the number of cycles per second. So this graph shows the graphs of voltage and current that vary sinusoidally with time. Now, if you'll remember that V is equal to IR, that the voltage and the current are going to be directly proportional to one another. You can kind of see that here. As they both drop to 0 here, you can see where they're both positive here. You can see where they're both negative here. And you can see how this current varies, and you can see the voltage varies even greater on top of that, usually because resistance is going to be greater than 1, and when multiplied by the current is going to produce a voltage value that is greater than the current. You can also see here that one period here to here, crest to crest, trough to trough. And so you can see that the angular frequency is going to be equal to 2 pi times the frequency, or 2 pi times 1 over the period. So you can see here you've got current and voltage are positive in this section. Current and voltage are 0 right here, and you can see current and voltage negative all throughout here. Now, obviously, here in the States, commercial electric power distribution systems always use a frequency of 60 hertz, corresponding to an angular frequency of 377 rads per second. Similarly, a sinusoidal current might be described this way. This I is the maximum current or current amplitude. So to represent sinusoidal varying voltages and currents, we're going to use vector diagrams similar to the diagrams we use for the circle of reference with harmonic motion, if you remember back to section 11.4. And so in these diagrams, the instantaneous value of a quantity that varies sinusoidally with time is represented by the projection onto the horizontal axis, this. And then that's going to be of a vector with a length equal to the amplitude of the quantity, which in this case is going to be I. So these rotating vectors are going to be called phasors, and the diagrams containing them are going to be phasor diagrams. So this is a phasor diagram for the sinusoidal current. The length I of the phasor is the maximum value of I, and the projection of the phasor onto the horizontal axis is going to be that maximum times the cosine of omega t. So at time 0, I is going to be equal to I. The instantaneous value is going to be equal to the amplitude. And this is why cosine is chosen, because whenever the angle is 0 here, this is actually a positive value. That's what cosine will lend to you. If it were sine, they would both be 0, and that's not really where we want to start out with these. So it isn't a real physical quantity with a direction in space, but it's more of a geometric entity that provides a language for describing and analyzing physical quantities that vary sinusoidally with time. So we've got some problems here for you to work through. So we can describe and measure sinusoidally varying current I in terms of its maximum value. So we can denote I max, or just simply I. An alternative notion that is more useful is the root mean square value, and it's shown graphically here. We square the instantaneous current, little I, calculate the average value of I squared, and then take the square root of that average. So that's why it's called the root mean square, or RMS current. So even when this is negative, the squared is always positive, so this is never 0. So in order to describe that, we're going to graph the current versus time. You can see that going on there. We're going to square the instantaneous current given by this particular equation. When we do that, this is what we come up with. How does this graph change? Well, if we start out with an instantaneous current of 3, then that jumps to 9 when it's squared. If it's 0, obviously it's just 0. If it goes all the way down here to -3, again, when it's squared, it goes up to here. So rather than have something that goes above and below this particular axis, the square value here is always above. So next, what we end up doing is we end up taking the average or the mean value of this particular quantity, I squared, and that turns out here to be I squared divided by 2. And then finally, when we go through and we take the root mean square of it, this is the value that we come up with, which is this right here, this straight line. That's what this is referring to. This quantity right here is about right here. And you can see why that's the average, because about half of the graph is above, half of the graph is below. And so it cuts through right here. When we take the square root of it, then obviously it gets a little closer here to the horizontal axis. So you can see all of the relationships here as I graphically they are described, but these are the mathematics behind it. Same thing holds true not only for current, but also for voltage. And so the usual household power supply in North America, designed 120 volts AC, has a root mean square voltage of 120 volts. And so the voltage amplitude is going to be 170. So meters that are used for AC voltage and current measurements are nearly always calibrated for root mean square values and not maximum values. So this is a problem here that will sort of describe exactly what it is that we're looking for RMS, current in a personal computer. So the plate on the back of a personal computer says the machine draws 2.7 amps from 120 volts, 60 hertz line. So for the PC, what's the average current? The average of the square of the current, and then the current amplitude. So setting all of this up, we're given the current, the voltage, and the frequency, but we actually only need the current. So as we go through and we sketch the graph, the current as it is given to us, 2.7 amps, that's the amplitude. As we draw this around, we can see here how it varies. It's going to go up above, up to a certain value, and then down to a certain value as well. The fact that it is drawing, or we're referring to 2.7 amps is what it's drawing. This is going to be referred to as the root mean square. Since we're given that particular value, if we are looking to find the average, or the average of the squared value, we take I squared and divide that by 2. And then if we're looking to take the value here of I and draw the square value of it, you can see that there are no numbers given here, but the idea here is to take whatever this current is, square it. It's going to be much further up. And of course, it doesn't go below the axis of t here, or time. This value right here, I squared cut in half, obviously is going to penetrate all the way through, where half the graph is above, half the graph is below. And then when we take the square root of it, or we take the, pardon me, the root of this is where this value comes up from, which again is what is being referred to here. So the root mean square, again, let's see exactly what's asked. The average current. So the average of any sinusoidal alternating current over the whole number of cycles is 0. The average of the square of the current. So if we go through our calculations, we know what this particular value is. We know it's equal to the square root of the current squared average value. We know that this, if we take the square root of both sides, we end up with this. We know what this value is, and therefore the current squared average value is going to end up being 7.3 amps squared. So again, the RMS is going to be the square root of the mean of the square of the current. So if what we are looking for here is the average of the square of the current, that is going to refer to this value. For part C, the current amplitude, in other words, the value of I. The value of I, of course, is going to be the root I RMS is going to be the current divided by the square root of 2. So rearranging that particular formula, we come up with this. Since we know what the I RMS value happens to be, then we end up with 3.8. And here is a problem, a tutorial session that is set up to explain a lot of that particular problem. I'll let you run that on your own. And here is an application of this type of concept for a transcranial alternating current stimulation, helping to deal with Parkinson's disease. So you might have an interest in that.